2.1 is all about patterns and inductive reasoning. So we're going to look at these and see if we can come up with the next in the pattern. So this, we're going 1, and then we have 3, and 1, 2, 3, 4, 5, 6, 1, 3, 6. Next one's going to look like what? Something like that, right? We're going to have add 1 on each side and then add that next layer. What did we get for the next one here? 16. See how we did? Good. We're going times 2, times 2. Oh, it's not a multiplying one, is it? Right? Very good. So looking at these patterns, plus 1, plus 2, plus 3, plus 4, plus 5, and then plus 6 will be the next one, and so on and so forth. So this next one, we have a triangle, a square, pentagon, what was he missing? Hexagon, a regular hexagon. This is the number of sides. We have 3 sides, 4 sides, 5 sides, and 6 sides. Now this one, not adding something, but multiplying. So we have times 3, times 3, times 3, times 3, 160. 160. So how did we come up with the next one in that sequence? How did we come up with the next one in any of those sequences? Yeah. What were we basing our conclusion on for each A, B, C, and D? Yes.
Oh. The word just completely left my head. But like, basically using logic.
Logic. We're looking at patterns, right? We're looking at a pattern, right? So inductive reasoning drawing conclusions based on an observed pattern. Drawing conclusions based on some observed pattern. So much of what we want to do in math and in school in general is make conclusions, right? Be able to prove things. Right? Inductive reasoning, we're just looking at the pattern. The drawback for inductive reasoning is we can't always assume that the pattern continues on indefinitely in that same manner. Let's say, for example, we'll use my daughter, for example. She, the last 4 years, she's gained about 3 inches each year, right? In height. So she went from 36 inches to 39 to 42 to 45 inches. Right, so each year. So when she's 25 years old, right? Is this going to continue? No, she'd be a giant, right? If she continues growing at that rate. So even though we have a consistent observable pattern, right? We can't necessarily always conclude it will continue forever and ever. In disproving something, a stated conclusion or conjecture, we just need a single instance where that does not occur. So a counterexample is an example that shows a conjecture to be false. An example that shows a conjecture to be false. So, for example, what if I made this conjecture? All El Dorado High School students came from Mark. Is that true? So if you're going to say it's not true, can you give me an example, a single example, that would disprove that statement? Yes.
Many other kids came from the University of Ridge.
Very good. All you need to do is find a single kid or individual that went to Sierra Ridge, and that disproves my statement. That's a counterexample to the statement that all El Dorado High School students went to Mark. So let's look at example 2. For all real numbers x, the expression x squared is greater than or equal to x. Anyone come up with one spot where that would not be true? So for all real numbers x, the expression x squared is greater than or equal to x. A single example. This one's kind of easy. It's about fractions. Right? What if I take 1/2? Squared. Right? 1/2 times 1/2 is 1/4. Notice 1/4 is less than that original x. So fractions provide a counterexample for that conjecture. What about for b? For all real numbers x, the expression the square root of x is greater than 0. What about the square root of 0? Not greater than 0. So 0 is our single counterexample. What about this last one? See if you can go ahead and come up with a counterexample to this conjecture. If the product of two numbers is even, then the two numbers must be. The product of two numbers is even, then the two numbers must be. Think about that for a second. Can anyone come up with two numbers when multiplied together make an even number, and yet they're not both even numbers? 3 and 2. Let's see. 3 times 2. Does that equal an even number? Check. Are they both even? No. 3 is odd. So that is a counterexample to that conjecture. Okay? If the product of two numbers is even, so we need to come up with something where this is true, but this is not true. Okay? So we have the product of two numbers being even. However, the two numbers are not both even because 3 is odd. Excellent. Take a look at these patterns. See if you can come up with the next number in the sequence for these. These aren't in your note package. Just go ahead and take a look and see if you can come up with them. Just an example I threw up to get us more practice. What about this one? One's a little tricky. Anyone? What are these? Are perfect squares, right? 1, 0 squared, 1 squared, 2 squared, 3 squared, 4 squared. What about this one? This one should be easy. 8.5. What about this one? 1.0001. What's happening with this one? Dividing it by 2, so we're going to end up with 1.25. And then what about this one? Square root, square root, square root. Square root of 2. All right. So we're going to look at patterns in section 2.1 and inductive reasoning. But much of what we're going to get into in chapter 2 is deductive reasoning. We'll look at that in section 2.